So today we'll be looking at Chapter 10 on structure and synthesis of alcohol. The structure of water and methanol are very similar. We're talking about alcohol, so OH-bearing molecules are important. We already know in terms of the structure of water, you have a bond angle of 104.5. When you replace one of the OHs with a methyl group, that bond angle increases slightly to 108.9. They're both sp3 hybridized, and now with the carbon-oxygen bond, you have 1.4 angstroms in terms of length. OH same, 0.96. There are classification of alcohols. As you may guess, there's primary, secondary, tertiary, and aromatic. Primary, again, carbon OH is bonded to one other carbon. Secondary, carbon OH is bonded to two other carbons. Tertiary, carbon OH is bonded to three other carbons. And with aromatics, phenols, OH is bonded to a benzene ring. Here's your classifications. Tertiary being here, and phenol-like compounds being here. Again, primary, secondary, tertiary, and phenol shown here. IUPAC, in terms of naming alcohols, you want to find the longest carbon chain containing the carbon bearing the OH group, drop the ene from the alkane, and then adding all at the end. Number the chain, giving the OH group the lowest possible number, and then number and name all substituents and write them in alphabetical order. Here are some examples of nomenclature. Here's 1, 2, 3, propanol, right? It's at the 2 position, it's 2-methyl, 1-propanol, or the new convention, meaning 2-methyl propane 1-ol. Here's 2-butanol, right? This is 1, 2, 3, 4. The 2 position, butane 2-ol, and 1, 2, 3. So this should be edited. So this is 1, this is 2, and this is 3. 1, 2, 3. So it's 2-methyl, 2-propanol, or 2-methyl propane 2-ol. In terms of enols, the hydroxyl group takes precedence, and you want to assign the carbon with the OH lowest number and the name in ol, but you want to also specify there's a double bind by adding ene before the ol. So as an example shown here, this is 1, 2, 3, 4, 5. So this is 2-ol and then 4-ene. So this would be pent 4-ene 2-ol in terms of the new nomenclature. In terms of naming priorities, acids are the highest ranking, goes to lowest ranking halides. We've seen this before. So alcohols are right smack in the middle of all of those. And you're just going to have to memorize that. When the OH is part of the higher priority class of compound, it's named as the hydroxyl. So here's carboxylic acid and the OH group. So again, this is the priority. It's the first priority. So this would be numbered 1, 2, 3, 4. So this would be 4-hydroxybutanoic acid. There are common names of alcohols, and they're useful only for small alkyl groups. This 2-methyl propane 1-ol shown here is also, right, this is an isobutyl group, so this will be isobutyl alcohol. This is, in this case, is ceik-butyl alcohol, right? It's a secondary butyl group. And when we name diols, in this case, 2 numbers are needed to locate the 2 OH groups, and you're going to use diol as a suffix instead of ol, and so this would be, right, 1, 2, 3, 4, 5, 6, 1, 6 diol, so it's a hexane, 1,6-diol. Glycols are 1,2-diols or vicinal diols. The common name for glycols use the name of the alkene from which they're made of. So in this case, this is 2 carbons, so it's a ethane. It would be ethane 1,2-diol, but a common name would be ethylene, right? Glycol. And then here, this is propane 1,2-diol. This would also be known as propylene glycol. In terms of phenol nomenclature, the OH group is assumed to be on carbon 1. And then for common names of disubstituted phenols, you can use ortho for 1,2, meta for 1,3, para for 1,4. And methyl phenols are known as cresols. So here's an example. This is 1, 2, 3, 3-chlorophenol or meta-chlorophenol. This is 1, 2, 3, 4, right? This is 4-methylphenol or para-cresol. So in problem 1, they're asking to name this molecule via IUPAC naming system. So you want to find the longest carbon chain that bears the OH group. And so that would be this shown here, highlighted in green. So this would be 1, 2, 3, 4, 5. So 1 will be the hydroxyl group. And then 2 position, you'll have this isopropyl group or 1-methyl ethyl group, and then iodomethyl group because this iodine is on the methyl. So this would be 3 iodomethyl, 2 isopropyl, pentane, 1 ol. In terms of physical properties, alcohols have high boiling points due to the hydrogen bonding between the molecules. Small alcohols are miscible in water. However, as you increase that size of the alkyl group, the solubility decreases. So here's some examples of the boiling point comparisons of alcohol. Here's ethanol, here's diethyl ether, and here's propane. Alcohol has the higher boiling point than ether, than the alkane, because this can form hydrogen bonds, right? From on the H and the O, this only on the O, and this has none. So the stronger the interaction between the alcohol molecules will require more energy to break. That's why you have this higher boiling point. So in terms of physical properties of alcohols, table 10-2 in your textbook talks about or shows the different alcohols as you're increasing in size as well as increasing in number of the ols. Generally, as you increase in size in a linear chain, you're increasing the boiling point. Now, if you, increase the substituents, that lowers the boiling point slightly. However, the general trend is as you're increasing the length, you're going to increase the boiling points. In terms of solubility in water, your table 10-3 in the text shows as you increase the chain length of the alcohol, it goes from being miscible when they're short chain to being less and less miscible as you increase the size of this hydrophobic region. Methanol is also known as wood alcohol. It's produced industrial from the synthesis gas. It's used as a common industrial solvent. There's a toxic dose, 100 mils. It's used as a fuel in Indianapolis 500. Fire can be extinguished with water. High octane rating, low emissions, low energy content, and invisible. Ethanol can be produced by yeast through fermentations of sugars and starches in the grains. You can generate 12 to 15% alcohol, and once that happens, the yeast cells end up dying. You can distill them so that you can produce hard liquors as an azeotrope of 95% ethanol. Denatured alcohol can be used as a solvent. Gasohol has 10% ethanol in gasoline. The toxic dose is 200 ml. In terms of the acidity of alcohols, the pKa ranges from 15.5 to 18, water being 15.7. Acidity decreases as substitution on the alkyl group increases. Halogens, other electron withdrawing groups, increase the acidity. And phenol is 100 million times more acidic than a cyclohexanol. So if we look at table 10-4 of Kas and pKs, going from methanol and increasing it to phenol, and then comparing it with water and other acids shown here. Again, range goes from 15, increasing, and then also when you go to phenol, decreases to 10. But essentially, as you're increasing the size, you're increasing the pKa. Water, again, is 15.7. And then acetic acid is about 5. Hydrochloric acid, -7. So you can see how they compare to these other. So in terms of a formation of alkoxide ions, so an alcohol in the presence of sodium, what sodium will do is will want to pair up with the alcohol. The hydrogens will come off, forming hydrogen gas to generate that. And so, for an example, in the presence of ethanol, sodium metal, you'll generate the sodium methoxide and hydrogen gas. And as a result, you generate this product, which is a strong base, right? We've seen sodium methoxide used for E2 elimination. More hindered alcohols like 2-propanol or tertiary butanol reacts faster with potassium instead of sodium. Now, phenols have a lower pKa of 10. As a result, instead of using sodium metal, you can actually use a base like sodium hydroxide that will pluck off that hydrogen. Electrons will go to the oxidant, generating sodium phenoxide and water, right? And this is where pKa comes into play, right? So pKa of water is 15.7, whereas the pKa of 10, phenol is 10. So as a result, the arrow will move or will go to favor the formation of the phenoxide. And the reason why it does is because of resonance. So this is showing the resonance again. In order to be true resonance, we have to put them in brackets. So that's what we're doing now. So you can take your electrons from the oxygen, have them come down, then push the electrons from the carbon-carbon double bond over here to this carbon. This can go push the electrons all the way around until you get to all 4 possible resonance form. And the true structure essentially is a hybrid of all these forms. So in terms of synthesis of alcohols, this is going to be a review because we've already learned many of the reactions. So one way we can form the alcohol is do nucleophilic substitution, SN2 of an alkyl halide with an alkoxide, right? We're going to say RO minus. You can also do addition of water to double bonds, right? We just learned that in 2 chapters ago. Producing alcohols, water and acid solutions, right? That will allow you to form carbocation intermediates, and then as a result, form the alcohol. The only thing that's a negative is that it suffers from rearrangements, right? You can have hydride shifts or methyl shifts. Oxymercuration, demercuration, right? That's HGOAC2 reaction, right, that we've talked about before, hydroboration, oxidation, BH3, sorry, please bear my handwriting, H2O2, and in this case you have anti-Markovnikov, in this case you have Markovnikov addition. This is also Markovnikov addition. Synthesis of vicinal diols in terms of review. Vicinal diols can be synthesized two different methods, right? You can have the syn hydroxylation of alkenes, right? Osmium tetroxide, hydrogen peroxide, cold dilute basic potassium permanganate. Remember, if we have it not dilute but concentrated and hot, this now ends up over-oxidizing alkenes to form the carboxylic acids and ketones. So remember that this has to be cold dilute. You can use anti-hydroxylation of alkenes, peroxy acid, followed by hydrolysis, so making the epoxide and then opening it up. And in the presence of acidic water, it would be this reaction. The other way that you haven't learned yet to generate alcohols are using organometallic reagents. So carbon is negatively charged, so it is bonded to a metal, magnesium or lithium. We'll attack partially positive carbons in the forms of alkyl halides as well as carbonyl compounds. And when it attacks carbonyl compounds, it'll form alcohols, or alkoxides first and then alcohols. Essentially, these organic metallic reagents can form carbon-carbon bonds. So, let's take a look. So we've already learned the reaction of taking an alkyne. In the presence of sodium amide, it forms sodium acetylide and ammonia. So once you form that sodium acetylide, this is your nucleophile, right? That nucleophile can then react with an alkyl halide, kick that off in an SN2 reaction, and form an alkene. So this is a carbon-carbon bond forming reaction. You can see, take that same acetylide, react it with a ketone or aldehyde. It'll react with the central carbon. Electrons from that double bond will go to the oxygen, forming the alkoxide, and then in presence of protonated water, so I'm going to draw out H, O, H, and H. So it's a slightly positive charge, electrons. So electrons here from that oxygen will pluck off hydrogen. Electrons go to that oxygen. You generate water, H2O as a byproduct, and then the alcohol, right, shown here. Right, so this is showing that you can take terminal alkynes, right, so terminal alkynes in the presence of the sodium amide can be made into a nucleophile essentially, and then these sodium acetylates can react as nucleophiles for making new carbon-carbon bonds or making alcohols. Grignard reagent. So Grignard reagent is an organometallic. In this case, you're taking an alkyl halide, chlorine, bromine, or iodine. Note, there's no fluorine because those don't react. In the presence of a magnesium, what will happen is that magnesium will insert between the carbon bond and the halide. This is just diethyl ether, which is just a solvent, generating this organomagnesium halide, otherwise known as a Grignard reagent. What's important to note is that this has a partial positive charge, this has a partial negative charge, and it reacts as if this is R with 2 electrons and negative charge, so that this is your nucleophile. right? And then this is just the remainder salt, like a sodium salt, but in this case is magnesium halide. Again, ethers are used as solvents, and they may be formed from primary, secondary, or tertiary alkaloids. Here are some examples of formation of Grignard reagents. Here's your alkyl halide in the presence of magnesium and ether. The magnesium essentially inserts in between, and what you're generating is literally you're generating your, right, this, and then MgBr, and this would be positive charge. So you can denote it as below, or if this makes it easier for you to see, then like your nucleophile being here and then MgBr here. Again, this would be 1, 2, 3, 4. So this is your electrons here, and then MgBr. Okay. Organolithium reagents. You can have an alkyl halide where you have chlorine, bromine, or iodine. 2 equivalents of lithium. Again, lithium will break this bond, forming lithium halide, and then your organolithium, right? So again, it reacts like R minus lithium salt. So that's why you need 2 equivalents. It reacts same way as Grignards, can be produced from alkyl, vinyl, aryl halides, just like Grignards. And ether in this case is not necessary, you can use different salts. So when you do addition, like we had shown with the acetylids, you can use Grignard or your organolithium. Here's your source of electrons, right? Will attack the carbonyl, kick off electrons to the oxygen, generating your magnesium alkoxide salt. Right, this happens with carbonyl carbons because it's partially positive. Once you have the alkoxide, right, so this can be also with lithium, organolithiums, but in general, right, it's R minus, attack, electrons go out. Once you generate this in the presence of water or H3O+, this will pluck off that hydrogen, generating your alcohol. So you can form primary alcohols using organometallics. Here's a Grignard reagent in the presence of formaldehyde. Again, you can redraw them as R and then MgX plus. So here your electrons will go to the electrophilic carbon, electrons go into the oxygen, you form the alkoxide, and then on the presence of H3O, the previous case it showed the example with H2O, you're going to have electrons from your oxygen pluck off the hydrogen, neutralize that positive charge, generating the primary alcohol in the end. So we're going to stop here and continue with the second half.